Hello, I'm Paul Hovaerts from the Eargroup, and I'd like to give you an impression and some results of cochlear implant fitting at the Eargroup by means of artificial intelligence. If you would come to the Eargroup and attend a cochlear implant fitting session, this is what you would see. This is our fitting room, or one of our fitting rooms. This would be the CI recipient, who is wearing the CI, would be sitting in front of the audiologist. The audiologist would open Audiqueen. Audiqueen is a software to manage the clinical data in an ENT department. If the audiologist would like to do one or a number of audiological tests in this patient, he would select them from Audiqueen's ribbon or menu and then drag and drop them into a basket. The basket would contain several tests, and so here the audiologist has chosen to test the right ear. The right ear should be wearing the cochlear implant. The left ear should be naked during the test. The audiologist may have changed some of the settings, and then he has decided that this patient can do the tests in self-test mode. He then picks the audio interface to be used, and he can choose. He can take an audiometer, or he can take an amplifier and speakers, or he can take the AutoCube, but in this case he has chosen the Coala Link. And the Coala Link is this wonderful direct connection between the computer and the processor. So you connect both by means of two cables. One is the programming cable and the pot, and the other one is the audio cable. And by means of this, you can perform audiological tests directly on the processor. So there is no need for a sound insulated booth. There is no need for audiometers. Everything is run at your desk from your computer. And then he clicks on start, and the patient can start doing the test on her own, while the audiologist can actually leave the room and have a cup of coffee. The interface for the patient is a simplified, very user-friendly interface which comes with ACE. ACE is, as you just saw, integrated into Audiqueen 3. And the patient can perform the test. It would typically take 10 minutes per test. So in her basket there were 3 tests now, so this would typically take half an hour. Then the audiologist comes back in, has a look at the results, and then opens FOX. FOX stands for Fitting to Outcome Expert, and it's this intelligent agent, so this piece of software which contains artificial intelligence. FOX will pick the map, R16, will analyze it. So FOX will then give a report saying that he has analyzed R16. This outcome, audiogram, loudness scaling at 250,000 and 4,000 Hertz, and speech audiogram. And he says, I have created a new map. You may have a look at it, and if you like it, you may save it and put it into the patient's processor. And that's what the entire fitting session looks like. And this is what we call target-driven, computer-assisted cochlear implant fitting. Now, this is quite different from the current state of cochlear implant fitting, where you would use proprietary software from the CI company. You would need quite some resources, expensive sound insulated rooms, audiometric equipment, very experienced personnel, and we have been conducting a worldwide survey in 2012 where we wanted to know how the current state of the art looked like. And for that purpose, we interrogated some 50 CI centers with a lot of experience in CI fitting. We invited them to come over to Antwerp for a 2-day debate, and the results were published. And some important results were that the field mainly modifies T levels and C levels, but hardly changes any of the other available parameters. That they do this based on the comfort of the patient. So the typical situation would be the audiologist sitting in front of the patient and then asking whether a sound sounds comfortable or not. He would then change some of the map settings and ask again whether this is sharper or less sharp, or more agreeable or less agreeable. And the more comfortable map would become the take-home map. And this yields huge variation across professionals. For instance, we did a cross-sectional examination in a number of centers. This was for a cochlear device, but we have similar graphs for the other devices. And in each center, we looked at a number of patients and at their map settings. In green, you see the T levels in all these patients, and in red, you see the C levels in all these patients. And what you see is that in some centers, patients would systematically receive very low T levels and very low C levels, whereas in other centers, they would systematically receive very high T's and C's, and anything in between these two situations would also occur. But it means that in this center, a patient typically receives T levels which are higher than the C levels which the same patient would receive in this center. This is very remarkable indeed. And so this is what made us believe a number of years ago that there was room for optimization. And in order to optimize this process of cochlear implant fitting, we went and looked at other types of optimization, and they all are quite similar. Optimizing a process is like optimizing the process of heating a room. You can use a fire, you can use wood, you can do this manually, and in the hands of an expert who has good knowledge of all this and some experience, this can yield quite good results. But we have learned that it can be optimized by introducing 3 components, and these are very essential and general in any optimization process. There is the need for a sensor to assess the state of the system. We need an actuator which is capable of changing the state of the system, and we need a controller which reads the results from the sensor, knows the targets, knows the actuator, and knows how to drive the actuator to bring the system to target. And this is exactly so for cochlear implants. The sensor obviously is not a thermometer. The sensor should be a measurement which gives a good idea of the cochlear functioning. And for that purpose, we use the A psychoacoustic test suite, which contains a number of tests which are quite relevant in evaluating the state of the aided or the implanted cochlea. Now you can say that if you need to do a lot of testing, this is cumbersome, because exactly this takes time. You need experienced personnel, you need expensive equipment, and that is exactly the reason why we developed ACE Coala, to be able to get rid of all this expensive material, and the audiologist can just perform the test with the patient sitting in his desk. And it's also the reason why we have developed the self-tests, now available on Windows platform, but soon available on Android platform, and we will surely develop them also for iOS platform, which means that the moment will come where the patient will be able to do these tests anywhere, with a direct link, the Coala Link, connecting the processor to the tablet or the computer, and he will hear the sounds in perfectly controlled and calibrated conditions. This brings us to the actuator. The actuator in our case obviously is the cochlear implant, whose task it is to convey the acoustic information into electrical code on the acoustic nerve. We have put a lot of effort in understanding the behavior of cochlear implant processes, and for that matter we have developed this uniform graphical model to model the behavior of the 4 different implants in 3 domains: the acoustic domain, where the dimension is dB SPL, the electronic domain, where the dimension is dB full scale. This is what is happening in the electronic circuit, in the chip of the processor, and the electric domain with the dimension nanocoulombs or clinical units depending on the processor, and this is what is happening at the level of the electrodes. This is the current, electrical current, as it comes out of the electrodes. Now we have modeled this in these 3 domains. These are the 2 transfer functions. It is a dynamic or an interactive software application, and we have plotted the impact of the different map parameters on top of this, and in the dynamic application you can play with these map parameters, and you can see how the transfer function changes when you change the map parameters. And then we have developed the controller. The controller is FOX. It is the intelligent agent, stands for fitting to outcome expert. And FOX contains the logic. It reads the results from the ACE tests. It reads the map parameters, and then he will try to improve the map so that the measured results get closer to target. FOX has been proven to be capable of bringing a patient closer to target, and this is a set of results which has been published, and this has shown that the average patient will reach 90% of the measured points to be on or almost on target, with a quite small variation. So it's quite robust. It has also been shown that reaching these targets has a good impact on speech understanding. This is a study which has also been published, and by means of which it was shown that there was a significant difference between the Fox approach and the typical approach. It was a randomized prospective trial where half of the patients were assigned to the control group and half of the patients were assigned to the Fox group. And the control group received the typical manual fitting in the center. The Fox group received the target-driven computer-assisted fitting. The endpoint was set at 6 months, and speech audiometry in quiet showed a significant difference between the Fox group and the control group in favor of the Fox group. This was also shown in speech understanding in noise. But this all was achieved with the first generation of Fox, which relied basically on deterministic logic. A second generation was built, which used probabilistic logic. And I will give you a glimpse of how this looks like. Probabilistic logic, the building block of it is like this. If a certain condition is met, for instance, if a certain stimulus is perceived as too soft, then a certain map change, delta M, may yield one of different results. For instance, sound may be perceived as okay now, or it may be perceived as too loud, whereas it was too soft before. With a new map, it may sound too loud, or it may still sound too soft, or it may even sound softer than before. Each outcome can be appreciated as or in relationship to the target. And this is done by means of a metric which is called utility in artificial intelligence. So if the sound was too soft and if it becomes okay now, then this is highly appreciated and the utility will be large. And the same is for the other possible outcomes. And the combination of these utilities with the probabilities can yield an aggregate utility or a global utility for this map, which basically tells us that if you would give this map to 100 similar patients and say that in 80 patients the result would be okay, and in 15 patients the result would be too loud, etc., that taking into consideration all these possibilities, this is the global appreciation we attribute to this new map. Now the nice part is that you can ask your computer to calculate this not for just one new map, but for a number of new maps. And each map will come with its utility, they can be ranked, and the computer can then return the map with the highest utility, which is the map with the highest likelihood to be beneficial to this patient. And this is exactly what happens. So if you enter a certain result into Fox, say this speech audiogram, then Fox will create new maps. He will present one new map to the audiologist and he will give his prediction of this new map. So he will say, with this new map, your previous score was 60%. I think there is a probability of, I don't know, say 35% that the new map will give a result in the same neighborhood, in the same region, between 50 and 65%. There may be a probability of, say, 50% that the score will be better. It will lie between 65 and 70%. And there is a probability of, say, 15% that the score will be much better, lie between 70 and 100%. And he will give this probability for the second point, for the third point, for the fourth point, and for all 60 points, basically. And then you can measure this result again, And you will find very often that the new measurement lies within the predicted range and quite often spot on. And this really shows the power of Fox. On top of that, if you enter this new measurement back to Fox, he will compare it with his predicted measures and he can learn from it. The underlying tables and networks can change based on this experience. So there is an intrinsic learning effect which comes with this type of artificial intelligence. And this shows, for instance, in a case like this, a patient who has really very excellent results. One would say hard to improve. Fox will analyze these results and he will confirm this. He will say that the speech results are very good and you may choose not to change this winning team. Nevertheless, he says, I've analyzed 24 million new maps and I think I have found one which may yield even better results. So if you are ambitious and time permitting, you may try it out. And in this particular case, we did it and we found indeed slightly improved results. Taking all this together, these are our current results as obtained in all our postlingual deaf patients and who came for their annual control in the first 6 months of 2016. And you show that on average they have a score of 86% on an open set monosyllable word list, CVC list, which is the NVA, it's in Dutch. So this is a high score, it goes up to 100% with a relatively narrow spread, which means that it's quite predictable to get such results. It's even better in the very young ones. This is also a recent analysis in all children with congenital deafness who received an implant in their first year of life, on average at 10 months of age, ranging 5 to 11 months of age, and who now have an age to be capable of performing an adult speech audiometry, open set monosyllables. So 6 years of age, minimally, ranging from 6 to 16, on average 12 years of age. These are the results in these kids. 90% with a very, very narrow spread. So almost all kids have these good results. This is the subgroup with the cochlear, a nucleus implant, and this is the subgroup with an AB implant. This is not significant, the difference. And this led me to write this contribution to a recent supplement of Cochlear Implant International, where I said the results which we obtain nowadays are really comparable with results obtained in people with a hearing loss who are using hearing aids and who have unaided thresholds of 50 to 60 decibels. So it's really important to realize that results with the cochlear implant can be that good. We believe that this is attributable to Fox. These were our results back in 2008. On average, our patients had 57% or so easy. Easy is an index, which is the average of these points. It's the weight average. So we take the result at 40, 50, 70 is taken twice, and 80 dB SPL presentation level. And so this average is what we call easy, and it was 57 back in 2008. Over the years, it improved. Now it is 77, so 20% better than 8 years ago. And if we draw a line through the medians, then we recognize two slopes which coincide with the introduction of Fox first generation back in 2008, 2009, and Fox second generation 2014, 2015. So this already is a good indication that it may be attributable to Fox. One can argue that it's due to the upgrade of CI processes, because in these 8 years, many patients received an upgrade. So we looked at this. 4 cases got an upgrade from 3G to Freedom. On average, their easy went down with 3%. 5 changed from Auria to Harmony. On average, easy +5. 14 moved from Freedom to CP8 or 900, on average -1. 20 went from Harmony to NIDA, on average +2. So these figures are way too small to explain this 20% improvement. Another piece of evidence comes from a recent evaluation where we looked at patients who have very good results and who came in for their annual follow-up now recently in 2016, 25 consecutive patients, otherwise unselected. They had to be long-term users. On average, they were using their implant for 10 years. They had been fitted last year by means of Fox with the knowledge, the Fox knowledge of 2015, and they had received the best map then. They had been wearing it for 1 year. They came in now, and we did the speech audiogram with this map. This was entered into Fox, and we asked Fox whether he could improve this with his current knowledge, 2016. And these were the results. In dark green, you see the results with the map, their home map. And in light green, you see the results as obtained in the same session with the modified map. These are the within patient improvements where we saw that at all presentation levels, there was a significant improvement of a couple of percentages, but this only stands for 1 year incremental improvement. So when you see this, it is quite plausible that over 8 years they have an average improvement of, say, 15 or 20%. So to conclude, I think that with this approach, we have seen a speech understanding of +20% in 7 to 8 years' time, and that in my opinion, it is thanks to this approach, which is target-driven and computer-assisted, where targets are assessed by means of the ACE psychoacoustic test suite, and computer-assisted refers to the intelligent agent Fox.